All right, Marauders, in this video, 5.7, Enthalpies of Formation, we're going to look at how enthalpies of formation can be used to find the enthalpy change of a reaction. It's kind of similar to Hess's law that we talked about last time. Hess's law is that if we know several reactions that can be added together and we know their enthalpy changes, then we can find the enthalpy change of another reaction by adding together the enthalpy changes of those known steps. So same kind of thing, but here we're going to be using something called standard enthalpies of formation. And the notation we use is delta H, little degree sign, and then F. So this means that standard conditions, and this is for formation. So the enthalpy of formation, what it is the enthalpy change needed to make 1 mole of a compound from its elements. So since it's making a compound from its elements, then for any element, the enthalpy of formation is 0 because there's no reaction needing to take place. And so we have tables that we have values for all the standard enthalpies of formation. They've been calculated or measured in a lab for us, and we can use those to find enthalpies of reactions. So standard enthalpies of formation will allow us to calculate the enthalpy change for reactions that we're interested in. And basically the reaction equation that we're going to use is this. To find the standard enthalpy change at standard conditions of a certain reaction, we're going to add up all the enthalpy changes of your products minus all the standard enthalpies of formation of all your reactants. So basically what it's looking like, here's an example. If you had this reaction right here with methane and an oxygen burning to make carbon dioxide and water, and you wanted to find the enthalpy change for that reaction, we can imagine that reaction happening in a couple steps. Okay, so you could have your reactants, the oxygen and the methane, and you can imagine the methane being broken apart into its elements. So that's carbon and hydrogen. The standard state for hydrogen is diatomic, so it's talking about breaking these apart and forming H2 molecules. For oxygen, oxygen's already an element in its standard state, so it really doesn't have an enthalpy of formation because it's already an element in its standard state. And then if we take these elements and we make the products, so the products of this reaction are carbon dioxide, so that's taking carbon and oxygen, taking those and forming carbon dioxide, and we know the enthalpy change for that. And then taking the hydrogen and oxygen, using those to make waters, we can find the enthalpy change for that as well. So these values right here, you'd be looking up in a table. But basically, this is just a variation of Hess's law, where we are imagining that the reaction takes place by breaking everything apart into its elements, and then taking those elements and reforming your products. All right, so here is an example. It says, use the standard enthalpies of formation to find the enthalpy change for this reaction. So we have C2H4, and it's reacting with 3 oxygens to produce carbon dioxide and water. And what we're needing to do is use this equation. So you're going to take the enthalpy change of the reaction is going to be equal to the sum of the standard enthalpies of formation for all your products minus the sum of all the enthalpies of formation for all your reactants. Okay, so your products, carbon dioxide and water. So we'll do the carbon dioxide first. We have 2 moles of it, so we'll need to do 2 times. So 2 moles times, for carbon dioxide, it's negative 393.5 kilojoules per mole. And then plus the water, so we have 3 of those. And we would look this up in a problem on a test or something. It would be given to you like this. On homework questions, you might have to look it up in the table in the back of the book, or during a lab, you'd have to look it up in some kind of reference, like the back of the book or online. And so for water, you can find out, make sure you're looking at the right state. So this water is a liquid, so you want to make sure the water we're looking at in the table is also a liquid. It's going to be different if you use water vapor. So we have, let's see, 3 moles of that, and the water is negative 285.8 for its enthalpy of formation. Okay, so these are all your products. And then we're going to subtract from that the sum of all the enthalpies of formation of our reactants. Our reactants, we have C2H4, which is negative 74.8. We only have 1 mole of that, so we don't need to multiply it by any number of moles. And then we have 3 for oxygen. Oxygen, remember, is an element, so it may not be given to you in the table. You may need to remember, or you should remember, that for any element in its standard state, the enthalpy of formation is going to be 0, because the definition of enthalpy of formation is the enthalpy change to take that compound and or take elements and make that compound. So that doesn't that's just a 0. And so we'll add these together, and when you do that, you get an enthalpy change for this reaction of 1,569.6 kilojoules, and that will be negative. This is an exothermic reaction. It's a combustion reaction, so it's releasing 1,569.6 kilojoules of heat every time this reaction takes place.